we are almost done with homework 1 in our thermodynamics 1 course. We're on problem number 8. And so again, homework 1 is on basic things like properties and phase diagrams, steam tables, that kind of thing. But we also did stuff from chapter 4, which is molecular level interactions, equations of state, and a little bit of ideality things. Okay, so the homework question number 8 is one I designed myself on molecular perspectives. And so it says, find a picture of acetone. Okay, so we have acetone, so CH3, C, oxygen, CH3. I look at the picture, you can find your own picture. It's a planar molecule, okay? So, I mean that's drawn kind of what it looks like, basically. All right? Based on that, characterize acetone with respect to polarity, hydrogen bonding, and van der Waals context. Okay, so let's kind of pick those things apart separately. Okay, so polarity. Now, there's all those things we have to... So first off, we recognize the problem. Characterize the molecule. Okay, so that's the problem type. All right, and now we need to, have our molecule, and we have to kind of look at it. And now we're looking for molecular features to decide about its polarity. Okay, so when we're looking at the polarity, there was a couple things we talked about. We talked about double bonds and triple bonds. We talked about electronegative atoms like oxygens and chlorines and nitrogens. We talked about aromaticity a little bit. We talked about acetic hydrogens also. Okay, but let's see what we have here. Do we have an oxygen? Absolutely. Do we have a double bond? Definitely. Okay, now we have a double bond, not a triple bond. Okay, so we do have a double bond here. We have a triple bond. We also have these carbons, okay? So in terms of characterizing this guy, how am I going to characterize its polarity? I would say it's at least mildly polar, okay? At least. It might be, moderate, mild to moderate, okay? Polarity is relative because it's really like, you're comparing it to something else. So it's definitely not as polar as water, but it's definitely more polar than, let's say, an ether or an alcohol. Okay. So it's all relative, but I would say it's mild to moderate. But really what I'm looking for is, why did you come to that conclusion? Well, there's a double bond and there's an oxygen. Now, the reason why it's not, why isn't it strong is something you might want to pick up on. Okay, so let's back up a little bit. So if you said something, on a problem like this, if you said something mild to moderate because there's a double bond and oxygen, that would be at least in meet expectations, possibly in above expectations, but not in exceeds expectations or perfect. Okay, because what's missing? Well, what about these carbons? What role are these playing? So what role are they playing? They are neutralizing things. So if those were hydrogens, because this is formaldehyde or something, okay, well that's going to be more polar. Okay, so if this was an aldehyde, because that CH3 is a hydrogen, well that's going to be even more polar. Okay, but it's not. It's not an it's a ketone, and so those carbons are going to make it less polar because they're going to provide more putting to the thing, okay, in a sense. And that, the carbon won't be that starved because it has other carbons who are feeding it under the table while the oxygen's stealing the pudding. And you might be at home, if you're not in my class, being like, pudding, what is he talking about? Just bear with me. Electrons are pudding, okay? So we got polarity, mild to moderate polarity. All right. Let's think about hydrogen bonding, though. So what do we need to think about hydrogen bonding? Is it an acceptor, a donor, or both? And also its strength. Now, its strength is attached to its polarity, but not always just polarity. Okay. So, does it donate? Does it have a hydrogen to give up? Well, it has hydrogens, but those are not to give up. Those carbons are pretty neutral, okay? And they're not going to let go of those hydrogens, okay? Those hydrogens are really not acidic in any context. So I've got to assume it is not a donor. Okay. Isn't it an acceptor? Well, is there something that you can't accept with, lone pairs or something? And, a sense of polarity. Yeah, it's got this oxygen as an acceptor, so I call it an acceptor. Okay. Definitely not a donor and an acceptor. But it's an acceptor. Now I gotta ask myself, is it a strong acceptor, a weak acceptor, a moderate acceptor? Now, I said the polarity was mild to moderate. But I would say definitively, it's at least a moderately good acceptor. Okay, not mild to moderate. And you might be wondering, why? Well, the polarity puts it in that range. What makes it definitively moderate in this case is the accessibility of that oxygen. I can put a hydrogen here, or here, or here, or here. I have a lot more degrees of freedom associated with in terms of a hydrogen docking on that oxygen. Whereas something that is equally polar might not have as much room. Like, let's say if this was something like a nitrogen. Now, that's not a chemistry that exists, but, a nitrogen that has a hydrogen or whatever, okay? You get that nitrogen, well, but that nitrogen's in the way, and so it can't hydrogen bond as well, in a sense, okay? So that's how I characterize those two things. So, mild to moderate polarity, an acceptor, moderate, at least, okay? Now, the last thing I need to ask myself is, van der Waals, how does this thing pack? Okay? And what shape and size is it? Okay, well, size is easy to determine. I got 4 heavies. Okay? 4 heavies. Okay? And then the other thing is shape. Okay, well, it's trigonal planar. Trigonal planar. So it's a plane. Okay? And it's a triangle, okay? And so that's kind of how I would characterize this van der Waals shape. It's a triangle, it's planar, all right. So, but that's not the question, that's just kind of doing those things to set you up for the question. The question really is saying, acetone is basically nail polish remover. Okay? If you ever spilled under, nail polish remover is basically acetone. Probably written a little backwards, but anyways, if you ever spill it on your hands, they cool off because of all the evaporation. Acetone is about 4 times the molecular weight of water, okay, right? Because it has 4 heavies versus 1, okay? But it evaporates so much easier. If I spill water on my hands, yes, it evaporates, but nowhere near the rate of acetone, and nowhere to the degree of acetone. So based on this characterization, why is that? So let's draw in water here. Now, I'm not asking why water doesn't evaporate, okay? I'm really comparing my polarity and hydrogen bonding and stuff to water, okay? So first off, well, it's mildly polar, moderately polar, definitely compared to water, okay? So you have, if we kind of redraw this, like this, you got some minus here, and you got some plus here, and you got some kind of neutral E here. Okay, maybe. So if it's going to line up the charges, it's really going to kind of do it this way. Okay, so that the minus is with this plus and this minus is with that plus. Okay, which means that the 2 carbons don't really get good contacts. Or it's going to line up on top of each other and the charges don't really line up. Okay, so what you have is kind of these weak non-bonded interactions. There's really no cohesion between the 2 molecules. Because what does water have that it doesn't? It has hydrogen bonding with itself. It's a donor and an acceptor. Okay? And so that donor-acceptor capability is keeping it in the water phase. Acetone doesn't have that. It has this moderate electrostatics and very weak van der Waals. Because of its shape, it can't line things up well and have good packing with itself in conjunction with the charges. And so, even though it's a lot heavier, there's really nothing tethering it down. Okay, So it's kind of like I have, you know, two helium balloons, in a sense, okay? This one's made out of lead, this one's made out of rubber, okay? But the rubber one is like tethered to the ground, whereas the other one is just being, you know, like you put like a little pebble on the string. Yeah, it's gonna float away. Okay, so it really boils down to, no pun intended, the weak non-bond interactions, because it cannot have good van der Waals context and have good charge lineup. Okay, it's going to have one or the other. Okay, and because of that, there's not enough stickiness between two molecules to keep it in the liquid phase, so it evaporates right away.